Let's talk about notation. I use quite a lot of notation conventions that are my own. They're not unique necessarily. I didn't necessarily invent them, but I use them a lot because I find them convenient and easy. And I'll be using a lot of them in this course, so I figured I would probably introduce you to some of them so that you know what the heck I'm talking about. Just as an example, in statistics, if you want to indicate the expected value of a random variable, the usual way to write it is to put a great big letter E, often boldface type, and then some parentheses around the quantity that you want to take the expected value of. That's the common way to denote the expected value of a random variable x. I prefer to use angle brackets, and I put the quantity I'm taking the expected value of inside angle brackets. Now, as if that weren't weird enough in the usual sense, I actually use angle brackets in two senses. When I put angle brackets around a random variable, that means the expected value of that random variable. So if I put a left angle bracket, q sub n right angle bracket, that equals the expected value of q sub n, where q sub n is some random variable that we haven't yet observed. On the other hand, when I put angle brackets around observed data, I use that to refer to the average value of the observed data. So if I put left angle bracket q right angle bracket, that would just be the arithmetic average. Take all the q values, add them up, and divide by how many there are. So there are two different notational conventions here corresponding to two different uses of angle brackets. I kind of like it. You can use whatever notation you prefer. I'd like to introduce you to something that I think is extraordinarily powerful notation. Actually, there are several aspects to it. There's something called the abstract index formalism, and it really derives from the fact that we often refer to not just a single variable, but a group or a vector of variables. Suppose we had a time series, and it was the sum of some part which is deterministic and some part which is stochastic, essentially random. If it's the sum, we could indicate this by saying this equation, that x sub n, the nth data value, is some function of t sub n, that is a deterministic function of time, plus epsilon sub n, where epsilon is the random or stochastic part. In this equation, the n subscript, it refers to a specific single value of the observed variable x at a specific single value of the time t. And if this is true, if this equation is true for all n, for all values, what we really have is a separate copy of this equation that holds for every index value n. But sometimes it is very useful not to think about a single value of the variable, but of all the values taken together as a unified whole. In fact, there can be considerable advantage in treating the time series data as a vector, in which case it's even more advantageous to treat all the individual quantities as a unified whole rather than a separate set of numbers. We might even want to write some equations where we put something that indicates not just a single value, but the entire vector of quantities. Well, there is a convention, and it won't always be followed, and I'll probably be a little fast and loose with it, but I'm going to try and be consistent so that you can make more sense out of it. And that is something called the abstract index formalism. The convention is this. When I write a subscript that is a lowercase version of the Latin alphabet, like the n in the previous equation, that will indicate what it always indicates. It's an individual value of a time series, as it usually indicates that. So x sub n means the nth component of x. We may not know what n is, but it is a single number. If that equation holds true for an entire time series, what that means is that we have multiple copies of that equation, one for each index value. However, if I write a subscript that comes from the Greek alphabet, that's going to indicate not an individual member of the time series, but the vector of all values. So x sub n means the nth component of x, but x sub alpha doesn't refer to any specific component at all, but to the entire vector of components. So an equation like x sub alpha is equal to f sub alpha plus epsilon sub alpha. This doesn't tell us about individual components. It tells us that the vector x is decomposed into the deterministic vector f and a stochastic vector epsilon. Now this means that the equation x sub n equals f sub n plus epsilon sub n, that has to hold true for each individual component of those vectors, that is to say for each value of n, but it is a different equation. The second equation holds for each time index value, but the first equation is not a statement about individual values. Rather, it's an equality between two vectors. Now, the reason that distinction can be important is that a vector can exist even if you don't have components to it. To have components, you have to have a basis for your vector space. So if you want to write an arrow to or a vector to indicate what direction you're traveling, well, it would be this far east and that far north. Then you have components. But that's only because you chose a basis, namely east and north. But the direction and distance exist even if you haven't done that. So there really is a important distinction between a vector and its components. By the way, there are many notations for vectors. I could have chosen many different notations to indicate a vector as a whole. I use the abstract index notation because I like it. In statistics, often we indicate something as a vector by setting it in boldface type. So if I wrote x equals f plus e, that means the vector x is equal to the vector f plus the vector e. In physics, it's more common to put an arrow above a symbol to indicate that it's a vector. And here is the same equation in that notation. In quantum mechanics, you might put a vertical bar to the left and an angle bracket to the right and indicate vectors that way. Although things are a little different in quantum mechanics because they're generally complex valued quantities. So they're all the same equation. They're just using different notation. Do keep in mind that in the abstract index notation, the abstract marker, the alpha or beta or gamma or whatever, it is not an index. It's just a marker indicating the vector nature of the given quantity. So in the equation, if I write the equation x equals f plus e with little arrows above them, the arrows are not an index. They don't tell you which component. They're just a marker indicating it's a vector. The same is true with the abstract index notation, even though I'm using a subscript. That subscript doesn't mean a particular component. It just is a marker saying this is a vector. Now, this leads us naturally, by the way, to another very extremely useful notation that I love to use called the Einstein summation convention. It often happens that we have to sum some expression over all values of the time index, or all values of multiple indexes. For instance, suppose we have two time series x and y, and we want to add up the sum of all of their products. We would traditionally write this with a great big summation sign for n going from 1 to n of x sub n times y sub n. Well, that's great. That works fine. But there's another way to write it, and that is this. Whenever I use a Greek index to denote vectors, any index which gets repeated, used more than once, that indicates the dot product or inner product or transvection of the vectors. Computationally, it's the same as the sum over all index values. This is known as the Einstein summation convention. So the same equation we had before can be written just as x sub alpha, y sub alpha, meaning that I take x times y by components, add up all of those terms, and get a total sum. That can be thought of as a more abstract theoretical process, dot product, transvection, whatever. But the the Einstein summation convention means that I'm automatically doing that whenever an index from the Greek alphabet is used more than once. This, by the way, can be done in a lot of ways. For the inner product or dot product, if I'm writing with boldface type, I would write the vector x transpose times the vector y, which would matrix multiply them and end up giving you the sum. In physics, I would write X and Y probably with little arrows above them, and I would put a dot in between them indicating dot product. In quantum mechanics, I would put a left angle bracket X and then Y right angle bracket, and that would indicate the inner product of those two vectors, although it's a little more complicated there because they're complex valued. Traditionally in algebra, I would just write that great big summation sign for j going from 1 to n of x sub j times y sub j, but the notation I'll probably end up using most of the time is just to write vectors with Greek letter subscripts, and any subscript that is used more than once indicates that its usage is to be summed over all values. By the way, it eliminates the need to write all those repeated summation symbols. And after you become familiar with it, it may take a little while to get used to it, but after you do, actually I think it will help be clear about which variables are summed and in which way. We can extend this convention to multiple summations with multiple indexes. So for instance, the sum over j of the sum over k of the sum over n of m sub jk times c sub n times x sub j times y sub k times t sub n can be written by a simpler expression. Just use Greek letter subscripts instead, and understand that the subscripts that are repeated indicate summations over those aspects. Incidentally, when it comes to notation, these are some of the notations that I like and that I will use a lot of. I hope you get used to them, and I wouldn't be too unhappy if it became common usage. But when it comes to notation, you really should choose for yourself what works for you. In your private calculations, in your notebook, in your scribbling things to work things out, use whatever notation works for you. Don't stick slavishly to some notation because some book says it or because your teacher uses it. In publications, when you're writing something to be read by other people, you might want to forego your own personal private notation and instead use the notation that's going to be clear to your readers. But in your own private analysis, use the notation that really works for you. And this, by the way, is an aspect of the best notational advice I ever got, which is notation should be your servant, not your master.